Hello everyone, welcome to the course Introductory Neuroscience and Neuroinstrumentation. We have going through the recent advances in the field of neuroscience and neuroinstrumentation. I have discussed about epilepsy classification in the last week's module. So far, what we have seen mostly is non-invasive recordings of brain waves and all. So, for this particular lecture, we will be touching upon a very interesting topic that is invasive brain computer interface. What basically we'll be doing is I'll be discussing about how we can or when should we go intracranial, or when can we open our skull and take recordings for better insight. So all this thing we are going to discuss in this one short module. Along with that, we'll be discussing about, I'll show you one more concept which is known as a deep brain stimulation, when some particular electric pulses. So far what we were doing is we were recording electric potentials, or we are recording biopotentials from your scalp. Now what we'll be doing is we are providing a small current to your brain and observe the response. So also this is entirely one more new area of research which is known as deep brain stimulation. So, or direct electrical current stimulation, direct electrical stimulation, etc. So let's see first, step by step, why should we go for invasive EEG? What are the different implications of that? When should we go for the invasive EEG? When should we go for till which point on your head we should open? Like inside your head, in between your scalp and brain, there will be many layers. There will be dural, and after that there is a cortex, and then inside that there is a brain. So till which point you should go and when you should go. So all this thing we are going to discuss in this lecture. So first let me just give you an idea. So these are all the different BCI approaches which we have seen so far. So this is basically a non-invasive approach in which on your scalp you will put some electrode and obtain EEG. This is known as a normal conventional basic EEG. Now there is one more term, MEG. So MEG is magneto-electroencephalography. So we would have studied in our initial in our +2 or before that when some change in current happened, the magnetic field will get induced. So similarly, when currents will pass through your inside your head, or due to that neuroelectric pulses, there will be a small magnetic field above your head, which you should be able, which if we can sense that particular magnetic field, then it will give us some idea about the activity going inside your head. So this is somewhat a principle, one of the motivation behind fMRI as well. So there are magnetometers or SQUAD using which you can obtain the intensity of magnetic field and conclude more about compared to EEG. It has excellent spatial resolution and it has been used. I'll just show you a quickly illustration of MEG. So this is basically an illustration of MEG. As I mentioned, some electric current happens, as a result of that magnetic field will get induced, and we are measuring that. As simple as that. Whereas this is a 1020 system, a normal EEG recording which we have seen so far. If we go further deep inside your head, in that case we are taking a recording from somewhere this line near to your cortex, or at the surface of your outer surface of your brain. That is called ECOG. So nothing but electrocorticography. In other words, it is also known as IEG, stands for intracranial EEG. So if you see this image, it shows how intracranial EEG from where it is being recorded. So your skull, your skull will be opened. It's a minimally invasive process. then some electrode will be placed, and further we can record the response. Now, this is for IEEG. If we go further deeper inside the brain to take recording, there is something called SEEG, and which stands for stereo EEG, stereotactic EEG, in which what we are doing is this kind of incision would be made inside your head, and further electrode will be placed even deeper. If I talk about how much it would be, said it will be somewhere like here, as you can see. Further, if we go even deeper inside the brain, or there is one more a field of study to put bioresorbable implants inside your head. So what this bioresorbable implants or bioresorbable electrode does is, if you place this bioresorbable sensors or electrodes inside your brain with wireless transmission capacity, it can give you an idea about the neural activity happening inside your brain in real time continuously. So just for any subject with a brain disorder, be it epilepsy or anything, we are not able to record the responses, so that recording time is limited. You cannot put electrodes on a subject and record throughout. It's inconvenient, and you cannot record it for a longer duration of time. Whereas, so if you can place something like intracortical implant with bioresorbable material, very important thing, that material which you are using is bioresorbable. Otherwise, it might result in some form of infection, or it may hurt, it may damage some of the tissue, and as a result of that, you might lose your sensory system, or you might lose. So for implantation, or when you go inside your body and putting something, very important thing, that it should be biocompatible, bioresorbable. So I hope this different approaches, the first two approaches are non-invasive, and the next two approaches are minimally invasive. SEEG is invasive, and basically now we will see when these approaches are used. If you think like we are measuring or we are recording using EEG, it's simple. You are not supposed to open your skull, anything. Even once you have one proper headband or any kind of device, it is very easy for even a semi-skilled person to take the recordings and check it further. So why should we go, or why should we open the skull and go intracranially, or why should we go even deeper into your brain to measure the response? So all this thing, comparison behind these three techniques, and why should we go for IEG and SEEG. Additionally, how the parameters or affecting things will change when you go from EEG to IEG to SEEG. So we'll discuss this thing. So it's very important analysis or points which I have noted down. So consider this is your EEG. This is the like evolution, right? From EEG to intracranial EEG to SEEG. It's very clear now that EEG will be recorded from the scalp. ECOG will be somewhere near to your cortex, and SEEG would be deep inside your brain. So now let's see how it differs. So first, when we go from EEG to intracranial EEG to SEEG, the amplitude will increase. So very simple. Why? Because it has been already noted down that you have many layers before your brain, between your brain and scalp. So whenever you go inside, there will be some of the layers can act as an attenuator for biopotential. So whenever you go deeper inside your brain, then your biopotential's amplitude will increase. Additionally, each layer works as a low pass filter. So whenever you go deep inside your brain, that action of low pass filter, or finally your cutoff frequency, after which that skin layers will stop allowing biopotentials to go out of skull. So the cutoff frequency will get increased. As a result of that, you will get even higher frequency component. So these are the first 2 points. One more thing is, for EEG, you will find it's a recording from scalp, so you will find more noise. It also has this atmospheric dependency as well. Whereas if we talk about intracranial EEG and stereo EEG, there are compared to, and there are two things. One is that you are going deeper inside your brain, so you will get prominent response, amplitude frequency would be higher, and noise also would be lesser. As a result of that, you will be obtaining very nice SNR, signal to noise ratio. Further, if I talk about a field of view, or when I think about electrode design, there should be area of contact defined. Like basically, electrode is nothing but a metal body which will acquire, or which will allow some biopotential to transmit from your brain, the neural response from your brain to finally signal conditioning or calibrating unit. So the area of contact, whenever you go from your scalp to your deep inside your brain, there is a lot of cortical columns, plus there are so many like you have to consider brain anatomy while placing electrode inside your brain. So that area of contact for electrode, if I talk about electrode, there is a cross section or patch, so that patch of the electrode will get reduced. Additionally, the region or site of observation, when you will get reduced as well. Further, as you go deeper and deeper, your field of view and area of contact will decrease, as well as your spatial resolution will get increased, because your source, you are getting closer to the source. That's the most important thing. When you grow intracranially, or you are going for stereo EEG, intracranial EEG is also known as electrocorticography. So for electrocorticography and stereo EEG, you are going deeper inside your brain, you are going to near to the generator of your biopotentials. That's why your spatial resolution will increase. But and one more thing, why this is one of the reason why SEEG is used, or stereo EEG, for brain surgery and brain tumor detection, because you exactly need to verify, or exactly need to go to a particular tissue which has a tumor, and you have to remove it. One more thing, before going for brain surgery or brain tumor removal, fMRI is advisable, because that will provide you an exact location of where your tumor is. Further, you can go deep inside your brain and remove the tumor using SEEG. But when you go, as I mentioned, deeper to your brain, it is advisable to first have an image or a spatial distribution, and you should be exactly aware, you should be exactly able to locate your tumor or lesion inside your brain, so you can remove it properly. Another point is that tumor or lesion should be removed by some experienced neurosurgeon, because even a small change in terms of your movement, or even a small change in electrode, may hurt, or may result in lifelong adverse consequences. So when I go from a EEG again to IEG and SEEG, the invasivity, the incision, everything will increase. Another point is complexity, that is experimental complexity. When you go from EEG to IEG to SEEG, experimental complexity will increase. Like for EEG, if you want to set up your experiment, you can do it in 10 minutes provided your system is ready. Whereas for IEG, you need to open it, and it might take some time, as well as it needs expertise. And for SEEG, you need to place electrode, you should have a stereotaxic equipment which will precisely move your electrode across the skull. So when you go from EEG to IEG to SEEG, your invasivity and complexity increase. One more thing is for IEG and SEEG, you are opening a skull, so you need to provide some anesthesia. So now the influence of anesthetics, or some pain removal drugs, that is narcotic analgesic, will be higher when you go from EEG to SEEG. Now your EEG or scalp EEG also will vary with respect to your when you apply any anesthetics. But for scalp EEG, you don't have to give any kind of anesthesia, because it's a non-invasive process. There won't be any kind of pain felt by a subject. So for the other two techniques, like IEG and SEEG, whatever the response you are obtaining, that would be in influence of anesthetics and analgesic, but there are different kind of anesthesia available, which make sure that suppose there is a case when you need to get an idea about the sensory system, or get an idea whether a subject, you need to make sure that subject is not losing any kind of sensory system during the surgery. So in some of the complex surgery, you might have to take and check the functionality of sensory system during the operation. So in such intraoperative checks, what you can do is there is a specific kind of anesthesia available which will prevent some of the functionality of your sensory system, but making sure that other remains intact. So designing or working or setting an experimental protocol, setting a proper drug for a before brain surgery, during brain surgery, setting a proper drug for anesthesia is also an important task. And all this thing like your timings, your because each and every anesthesia will have its own recover time. So your entire brain surgery should be planned in such a way that subject will not be its sensory system will not be harmed, it will not have any adverse consequences, as well as that subject will not feel any kind of pain, and operation should be carried out properly. So anyway, this for MBBS students or any of the doctoral students here, after anesthesia, dural anesthesia is also a super specialization where specifically they will be taught only about anesthesia related to brain surgery. And last but important point, along with tissue damage, there will be a lot of infection. So when you put your electrode inside your brain, then there will be a or even for mostly for stereo EEG, the tissue will come into the contact of your electrode. So all this thing must be checked before taking recordings and all that. That interface between your tissue and your electrode must not harm the tissue itself. But yeah, the chances of tissue damage is higher when you go deep inside your brain. So now let's quickly see what are the applications and limitations of invasive EEG techniques. So first and foremost, brain functionality mapping. Second is extraoperative, means when like anything which has been done when operation is not under progress. But intraoperative means while operation you can check sensory outcomes of sensory outcomes, whereas in case of extraoperative thing, you can evaluate any surgery or epilepsy surgery evaluation or brain tumor evaluation. Further, you can also check, I have told one term, brain stimulation. So there's something similar, direct cortical electrical stimulation during the surgery. So you will give specifically pre-designed stimuli, that is nothing but a small electric current, and as a response to that your brain will show some response. So basically these all are applications mainly for when you have a critical case of epilepsy, you need to remove some of the particular tissue of your brain, or you found some brain tumor which can be life threatening. All these things can be removed with the assistance of invasive EEG techniques. So now what are the limitations of invasive EEG techniques? So first thing is recording time is limited. So you cannot place your electrode and open your skull and keep it there for longer duration of time. Additionally, you cannot make incision, or you cannot put electrodes in your entire skull. There should be a specific region. Whenever you perform any kind of surgery or this kind of recording, your focus should be defined, that your site of generation should be defined. So further, there is a risk of damaging tissue. I already mentioned that it might hurt the tissue as well. There are leakage of cerebrospinal fluid, as well as it might happen that you may receive some form of bleeding as well as infection. So all these things will be considered when you go from non-invasive to invasive EEG. So now we will see how to realize this kind of recording and what are the devices, instrumentation required to get this kind of recording. So I already mentioned that area of contact or the site which we are observing, which be much lesser, so that dimensions of your electrode would be in sub-millimeter range. So it would be few tenths of micrometers. So now, so far you have been taught a lot about microfabrication, like what are the thin film deposition techniques, how photolithography works, what are the characterization techniques. A few of the things have been touched up by Professor Pandya. So all this thing will taken into consideration when you are designing any of this kind of application. I'll quickly tell you about what this device mean and what does it look like. So first of all, idea wise, this is the entire one microelectrode. This is known as shank. So further, this is a zoomed in view of this shank here, and additionally, this is the final view of how these electrodes will be placed. So this shank will be inserted, or this shank will go inside your brain when you are taking intracranial or stereo EEG, and all these pads are your metal pads. So from metal pads you can take output from this blue square, and then you can analyze your biopotential. But all this thing is possible when you know what are the fabrication. For that, there are microfabrication techniques which has thin film deposition, which is thin film deposition basically has a physical vapor deposition and chemical vapor deposition. For physical vapor deposition, thermal evaporation and e-beam techniques and all techniques have been already explained in the course. For etching, there are different kind of etching. For CVD is a chemical way to deposit any kind of pattern onto silicon or any substrate. So this is actually a mask using which we have fabricated some of the microelectrode arrays for diagnosis of epilepsy and stroke. So these are the materials which has been used, as I mentioned, on silicon substrate of 200 micrometer. We tried to pattern this electrodes, and which metal is used, either you can use gold or titanium. So that separate study you can perform considering material property, but conductivity as well as heat resistance, all this thing is very nice when it comes to your gold or titanium, and there should be an insulation layer. Of course, for any microfabrication technique, you should be having one insulation layer to separate out silicon from your patterning layer. And these are the design specification. We'll not go into the detail of the design specification, but from numbers you will get an idea that a few micrometers is the gap between two electrodes. So further, if you go into the detail, you should be able to know that this is one shank. You can have multiple shank here as well, but the idea is you should also know in which site you are going to place this electrode, because inside your brain, your anatomy should also be taken into consideration, because that has its own shape. Things are placed when you go intracranially or inside your brain. Already there is a lot of nerves, and thing is there is a very small gap. It's in few millimeters, like 2 millimeters, 4 millimeters, not more than that, between the nerves which are going. And even a small incision or even a small damage to that nerve, as I mentioned, can result in lifelong disabilities. So this distances between the free space, I should say, inside your brain is very small. So considering all this thing, this shank's dimension should be design dimension should be finalized. As you can see here, the shank's width is around 200 micrometers, 0.2 millimeter, and such devices exist, and people have able to fabricate and obtain responses using that. So in our lab we are also aiming to get this kind of devices. This is just one of the devices which I have shown here, which is having 18 electrodes, multi micro electrode array, I should say. And this all the dimensions I mentioned. This is a shank width, this shank length is 3 mm. You can so this is your shank. You can operate your shank on which direction you want it to move using stereotaxic equipment, which has a precision of very, in terms of few micrometers. So that will make sure that you won't touch any of the uh, nerve or any of the tissue. You won't damage or infect any of the nerve and tissue. So additionally, this all are analysis, like you can what is the angle at the tip and all this thing. Once you go into the detail of the design of microelectrode array, you can consider all this parameter. So now I'll show you some of the designs. So this is basically uh, you can see we have seen micro needle. This is a microneedle with one shank. Same microneedle is placed here, wire bounded in some of the PCB. So this is the next step. Once you fabricate your device, that particular thing will be wire bounded and into some of the PCB. This PCB will have a signal conditioning circuit to acquire a particular biopotential. So as you can see here, this is already wire bounded PCB. Now further, how the entire microelectrode assembly will look like, or what are the rest of the thing required to finish the loop. What microelectrode does, it will record the biopotential from a deeper region of brain. What PCB will do, it will perform as a signal conditioning circuit. But after that, how you are going to transmit your biopotential from your PCB to the real world for finally any kind of conclusion where you are going to see all this thing. So that is basically the entire system based on microneedle microelectrodes. So I'll quickly show you the system or microneedle assembly. So it is something like this. So this EIB is electronic interface board. So this is basically your microneedle black part, whereas this is your PCB, wire bounded PCB, and the rest of the thing, drives and electronic interface board, is to acquire the potential from your PCB to the real world. And there should be a provision to precisely move your microelectrode. For that we will be having a stereotaxic stand, and this is actually the system on which which is being used for microneedle recording. So you have a PCB, micro drive, electronic interface board, and you have a stereotaxic stand. So this stand would be this would be connected to your stereotaxic equipment, and then once you move it in a particular direction, you should be able to navigate your microelectrode accordingly inside your deep brain region. So this is basically an idea, but as I mentioned, the key part remains this fabrication of your microneedle. Rest of the things are already existing in real world, but you should be able to know that how you can get this kind of design, for which all the basics of microfabrication is very important, so that you can pattern a desired way or desired number of electrodes with proper contacts in order to get the desired microelectrode arrays. So I hope this microelectrode portion is understood and clear. Now we will touch upon another very important topic, that is I mentioned brain stimulation, deep brain stimulation. So again, the acquisition part of microelectrodes remains the same. You can see this is one of the design, or of mass design I should say, for the fabrication of your electrode. All the images are shown. This part basically is your electrode. Again, the dimensions and all are provided, whereas the bottom part, this part, is nothing but your contact pad. If you can see, the length of your electrode differs here. So you can go based on the length of your electrode, height of your electrode, you can go in a particular region. So you have to decide how deeper you want to go inside your braid, and you can think about it. So here the substrate which has been used is polyamide, and material is used titanium gold. What is the diameter of electrode is 300 micrometer, and this is the sensing regions dimensions. So further, this is the actual fabricated image which I was talking about. And once you fabricate any kind of device, you should be characterize it properly. Like you cannot fabrication, microfabrication, as it suggests, there will be a precision in micrometer range. So you cannot directly say and evaluate any of the fabricated device. So for that, you must do somewhat characterization. So basically, there are many techniques for characterization. Electron microscopy, like SEM, if required, TEM. If your final precision is in a few nanometers range, you should go for TEM. But in mostly in this case, if you go for SEM, or if you want to see the consistency, or if you are making some kind of trenches and you want to see the consistency of that, how uniformly it has been deposited and all, you should go for optical profilometry. So there are many characterization technique to evaluate the fabricated device. So this is basically a fabricated device you can see here, and this is the actual images of same. So I have already shown you before that this is the target, or this is the mask using which will be used to pattern the device. So similarly, here you can see the same kind of structure has been obtained using a fabrication technique. So this is just to provide you an idea that whatever has been taught in the course of the this particular topic, this particular subject, that neuroscience and neuroinstrumentation has a lot of importance in even process like microfabrication has a lot of importance in the field of neuroscience and neuroinstrumentation. So yeah, this is basically, and one more point, that characterization is as important as fabrication process, because that will give you an idea of how successful your fabrication process is. So finally, which kind of current should be given? This is just an illustration that it is basically a combination of your microcontroller and your op-amp. So using op-amp you can generate any kind of pulse, but yeah, in microcontroller you can program it from the inbuilt timer. So based on your requirement, with some preliminary level electronic design, you should be able to generate a stimuli which can be used for your brain stimulation. I've already covered auditory stimuli and visual stimuli in one of the previous modules. The similar kind of approach is here. There we are using some software which has inbuilt timer. Here we can use some general purpose microcontroller and program your device and obtain the desired electrical stimuli or periodic electrical waveforms to obtain a particular brain stimulation. It has been studies have shown that if you provide any particular kind of stimuli, electrical stimuli, you will be getting you can navigate, or you can make a person do a particular thing. Like for example, if biphasic electrical stimuli is being inserted into rat's brain, you can able to navigate the rat in a particular direction. So if we talk about the application, a lot of application exist, not only just to check whether a person's sensor system and everything works fine during the operation, not only intraoperative but extraoperative as well as in real life. As I mentioned, you can able to move rat in a particular direction. Similarly, you just place camera or something, a micro camera on the rat's head, and you can move it. You can use it for spying purpose or any other thing. So there are a lot of application of tree-based stimulation, but the idea of this particular module is to inform you, or is to glance through the topics of multi micro electrode array or microneedles, as well as with a slight change or slight additional modality in microelectrode array, easily getting response which is in response to a particular stimuli. So I hope these two topics, microneedles or microelectrode arrays and brain stimulation, is clear to all of you. You can feel free and explore more about the topics to get a better idea. If you have any questions, feel free to ask us in forum. I hope this is clear and it will help you, and you'll be able to obtain more and more literature about this, and you can go through it. And as I mentioned, uh, feel free to ask questions regarding this in forum. Bye. Take care.